So this will be the first lecture on stochastic aspects, and I mean it as a very brief overview of some stochastic, some justification for stochastic models in epidemic modeling. And also I'm going to take the opportunity of this lecture to talk a little bit about residence times or sojourn times in compartments, because I think it's an important modeling consideration. So first, and that will be super brief, why would we need to use stochastic systems? And then, as I said, I will discuss a little bit the notion of sojourn times, which I think are very, very important in modeling and are not given as much attention as I believe they should. And finally, I will very briefly talk about the types of stochastic systems that we might be using. And in practice, we use only two of the several types I will be showing, but that's it. First of all, and as I said very briefly, because it is so evident that it doesn't really need a lot of explanation. So if you really want to look, to think about why it could be important to take into account stochasticity, well, the following sort of reasoning really explains where this is coming from. So if you think about what life is, well, it's the interaction of an enormous number of processes. So I was talking the other day in a previous lecture about how mobility is difficult to apprehend because of the scale at which it happens. Well, if you're looking at life itself, even you yourself as a human being, that dwarfs mobility by orders of magnitude in terms of complexity and the number of processes that are acting. And the important thing is that each process that makes up life can happen with some degree of imprecision. And we see these the consequence of this everywhere. So for instance, if you think about a virus that's replicating within your body, well, when it's replicating, every so often something happens. You miss something is badly transcribed. Or think about a cell that undergoes mitosis, when the material is not split 50-50. Or at a higher level, when people interact, I write, you forget to shake the hand of the person you meet, or like in COVID, isolation time, it might be the other way around. Perhaps you forget that you're not supposed to shake hands with the person you meet, and you actually end up shaking hands once. And so all of that means that all of those little mistakes that happen lead to a certain degree of uncertainty, and that uncertainty is typically well incorporated in stochastic systems. And so that's why altogether you can and should, in some instances, incorporate stochasticity in your models. And a bit, before I move on, a bit the same way as I've been stressing once you learn to use a hammer, every problem starts to look like a nail. Also, stochasticity is not necessarily needed in models, and so it's always a good idea to try to see if you really need to incorporate stochasticity, because stochasticity makes analysis and simulation more complicated. Okay, so there are situations where it won't be necessary to incorporate stochasticity. Use, as with all modeling methods, use wisely and try to reason why you are going to be using a certain method rather than another. Now, one thing that I want to do is to spend a little time talking about Sogern times. And the reason I think this is worth spending some time discussing is that, in effect, even the most classic deterministic model incorporates stochasticity. So most deterministic models are actually stochastic in some way. They just hide the stochasticity. Okay? And I think it's important to talk about this a little bit because this is really, it boils down to what is a model and what goes into a model, etc. And I think once you understand this, you're better equipped to see what it is that happens in the equations that you're using to describe a problem. Okay? And I'm not saying deterministic models have stochasticity. They incorporate stochasticity in a way that I'm going to explain now. Okay, so but you do retain the complete predictability with a deterministic model. Okay, but something in there is stochastic, and that's what I'm going to discuss here. So I really like to drive this point because sometimes when you're talking with other modelers, they will say, yes, but you haven't put stochasticity in there and it should be there. And really, I think it's important to understand what's happening. Okay. So to do this, let me explain a little bit some notions. And so this is going to be a very brief intro to some probability theory. Okay, and to start with, I'm going to take a very simple sort of theoretical mind model. So I'm going to assume that there is a system that I'm observing, and that system can be in one of two states, S1 or S2. And the system always starts at time 0 in state S1. And then something happens at some time tau, and that triggers the change in state of the system from S1 to S2. So this change in this state can be anything, and I'll come back to this. We're going to call random variable, and this is the typical, I'm not doing anything weird here, okay? A random variable is simply going to be a variable that takes random values. And so this is going to sort of map random experiments to numbers. And I'm going to call T, capital T, the random variable that I'm going to define by saying that's the time that the system spends in state S1 before switching to state S2. Okay? And the states can be anything. Okay? So the system can be working and then become broken. Or you could be thinking about someone who's infected and recovers from the disease. Or you're talking about someone who's alive and dies. Okay, so if this is a very, very common way of thinking, so for instance, I'm illustrating here. I remember when I was a student learning probability and statistics, all the examples seemed to revolve around how long a light bulb was working for, and we want to get some law, some model, and this is going to be a model, okay? We're going to want to make a model that describes this random variable t. And so what we do is that we take a collection of systems, so objects, that are in state S1, and we wait until they switch into state S2. And we want some way to describe this time of waiting. Okay? And from a sort of mathematical point of view, I can assume that I'm able to conduct an infinite number of such experiments. And each of these experiments, I'm going to observe the time that it takes for the system to move from one state to another. And that is going to allow me to deduce a model which is going to be a probability distribution. Okay. So the setting is something like this. So I have the arrow of time at the top. Oops, I am in front of it. I have the arrow of time here, and then I have a bunch of systems, infinitely many of them, and each one of them I let evolve through time, and I write down the moment at which the switch occurs. And this is T is going to be something that describes these durations of times between starting the experiment and switching into state S2. Now, very briefly, the random variables can be of several types, but the most common ones are discrete or continuous. And here, in the problem that's of interest to us, we're going to assume that the random variable is continuous. Okay, so that could be the height or the age of a person, if I'm able to measure it very precisely, but a distance, a time, and of course there's also a discrete random variables, but I'm not going to use them very much. But the same way as we can define continuous random variables, we can define discrete ones. Okay. Formally, probability is a function from the probability space to the interval 0, 1. And I'm not going to get into the details. If you're interested, then there are many probability good references about the theory. This is a fascinating area of study, okay? But this is not the objective of here, okay? I'm approaching the problem really from a user point of view. Now, if I have a continuous random variable, then one way that I can characterize this continuous random variable is using what's called a probability density function. And this is essentially the model that I have for my function. Okay? That probability density function is a function that is a non-negative function. It integrates to 1, because remember, as I was pointing out, the probability goes to 0, 1. It integrates to 1, and with a continuous probability density function, you don't have the weight of one point, but you get the weight of an interval. So, for example, the probability that my random variable is between A and B is obtained by integrating from A to B for a probability density function. The cumulative distribution function is simply the integral of the probability density function from -infinity to a given value. Okay, so if this gives you the probability that the random variable takes values less than or equal to the S that you're considering. Okay, and you simply integrate from that, and therefore this is the area under the curve from wherever your distribution starts to point S. Often we say T, so it's simply this integral. Now, the cumulative distribution function, because f is non-negative, capital F is non-decreasing, okay? And because I have a probability density function that integrates to 1 over the entire real line, my cumulative distribution function limits to 1 when t goes to infinity. Okay, so here I'm showing what some cumulative, distribution could look like and what the corresponding cumulative distribution function would look like. The mean value, the average, so let me move myself here. So what's typically called the average, but we call the mean. If I have a continuous random variable, t, and it has a probability density function, f, then the mean value of the random variable, which is typically denoted t bar or e of t, is simply the integral over the entire domain of t times f of t. Okay. Now, the one thing that we're going to be using a lot here is what's called the survival function. And that's another characterization of capital T, my random variable. And it's simply, so here I'm referring to the state S1 in my experiment, so S1 and S2. The survival function of my state here is simply given by 1 minus the cumulative distribution function. So remember, the cumulative distribution function gives you the probability that the random variable takes values less than or equal to t, or I think I wrote s here. Yes, S. Okay. The survival is 1 minus this, so it gives you the probability that your random variable takes values larger than t. And so that is going to give us a description of the time, so what's called the sojourn time, how long the system spends in a given state. Okay, so here we're looking at S1, how long until we switch to S2. This is going to be approached by using this survival function. So it's how long the system survives in S1 before switching S2. And because it is 1 minus a cumulative distribution function, it is this time a non-increasing function. It takes the value 1 at 0 and decreases the average sojourn time. I can compute and find that it's given by this quantity. And so the average sojourn time is simply the integral from 0 to infinity of the survival function. And we can also compute this this quantity, which is the expected future lifetime of a process that has survived up to t0, and we get it by computing this quantity here. Okay. Whoops. Yes, and finally, one thing that I want to point out, because I'm not going to be using it explicitly here, but it's a good quantity to sort of bear in mind when you're thinking about this type of problem, is what's called the hazard rate. So the hazard rate is the limit when delta t goes to 0 of, let's look at this one, this formulation here. This is that you survive to t plus delta t less than t plus delta t, given that you have survived to time t. Okay? So the hazard rate is the instantaneous probability of failure when you have survived to a certain time. So if you want to think about it, for instance, if you're thinking about the lifetime of an individual, typically kids, so mortality is highest in the years 0 to 1. So a hazard rate for a young kid would be slightly higher. And then if you've survived, or I mean, in places where there's no malaria, for instance, because if there's endemic malaria, then you might that might be shifted towards 5 years old, for example. But the overall idea is the same. So you have the survival in the first year or several years of life is not as given as it is later. So if you've survived to the age of 1 or 5, depending on the context, then for quite a few years, your survival, your instantaneous probability of failure, in this case death, is going to remain low. And then when you start aging, that probability starts increasing. Okay, so as you become older, if you've lived to 100, the probability that you will make it to 101 is much lower than if you've lived to 40 and survived to 41. Okay, so this hazard rate then re-increases, and we get something like I'm not showing you here, which is called the bathtub, typically called the bathtub survival hazard rate. Okay, so it starts quite high, dips down, remains low, and then starts to increase again when you age. So this is going to be, so as I said, I'm not going to use the hazard rate right there, but I'm going to talk about survival, and because I should point out, the hazard rate is simply the derivative of the log of the survival. So this is another way to think about these problems. Now, two distributions that I'm going to be focusing on right now are the exponential distribution. So this is a very, very popular and omnipresent distribution. So we say that a random variable t has exponential distribution if its probability density function takes this form. So it's 0 if t is negative, and it's theta times e minus theta t if t is greater than or equal to 0. And we take the parameter theta to be positive. So this is one of the most widely used distributions for a variety of reasons that I'm not going to go into right now. But so if you have a random variable that's distributed exponentially, then the survival function for that state that I keep on referring to is of the form e to the minus theta t. And the average sojourn time in the state is 1 over theta. And this should hint at things that I've been discussing throughout the course this far, but this I've said several times, that for instance, if your rate of moving out of I is gamma I, then you're spending on average 1 over gamma time units in I before you recover. And this is really where this is coming from, and you'll see why in a few minutes. Another extreme that I'm going to be discussing is the Dirac distribution. So suppose that I have, let me approach the problem this way. Suppose that I have a survival function for some random variable that is defined the following way. Survival is 1. So with probability 1, you survive for the interval of time between 0 and omega, some omega positive. And then past, for t larger than omega, then your survival becomes 0. Okay, so essentially, if you think of a system as being a human who's alive or dead, survival is with probability 1 on the interval 0 omega, and death occurs at time omega. And if you do that, then this means that the distribution that you're assuming for t is a Dirac delta distribution with parameter omega. And the average sojourn time is omega, but it's actually more than an average. It is a given. Okay, all individuals spend omega time units in S1 before they switch to S2. Now let's look at how we can apply this. So first is a cohort model. So sorry, I am in the middle. So let's look at a cohort model with a single cause of death. So a cohort is a group of individuals who are, for instance, struck at starting at the same time, but here I'm going to suppose that they're all born at the same time, t equals 0. Okay, so that's my cohort. So for instance, the same year, whatever. At time t equals 0, I suppose there are n0 positive individuals. I compound all causes of death together, and I call the time until death a random variable capital T. Okay. I'm assuming this capital T has continuous probability density function, f of t, and a survival function that I'm going to write p, capital P of t. So the model is a very, very simple model. If n of t is the population at time t, then n of t is equal to the initial population n0 times the survival function p of t. Okay? Because p of t, in a sense, if you want to, it gives me the probability, so essentially it gives me the proportion, in this case, of individuals that are still alive at time t. Okay, so it's the probability that you survive until time t, but in practice, for this, it gives us the proportion of individuals who are still alive at time t. So the model is this very simple model here. So I say n0 p of t, no, it's p of t that gives the proportion of n0. So n0 p of t is, yes, how much of the initial number n0 are still alive at time t. Okay. Now, let's look at this model, and let's assume that t has an exponential distribution. And I'm going to assume that it has an exponential distribution with mean 1 over d, or vice versa. Remember, the parameter was theta, and the mean of the exponential distribution was 1 over theta. So here I'm specifying the mean. I could also specify the parameter d. So that means this is the function for t positive, okay, t non-negative. For t negative, it's equal to 0. Then the survival function is simply e to the minus dt. Okay, we saw that formula earlier on. And therefore, if I replace in this equation, if I replace p of t by this survival function, what I have is this equation. Okay? But when I take this equation and I differentiate it with respect to time, what do I get? Well, the left-hand side is the derivative, and on the right-hand side, when I differentiate this with respect to time, I get a minus d n0 e to the minus dt. And n0 e to the minus dt is n of t. Okay, so when I replace n0 e to the minus dt by n of t, I get minus d times n of t. And of course, at time 0, I have n of 0. So what I have here is the differential, the ordinary differential equation, n prime is minus dn, which is like the ever-present, if you want to model a population in which individuals live on average 1 over d time units, and the only way to leave the system is to die, that's how you would write this. And so if you take things the other way around, if you think about it, this OEE, when we write it, we are making the assumption that individuals in the population have a life expectancy at birth that is exponentially distributed with parameter d. So that's quite important. There is stochasticity here. Of course, if I follow the solution to this equation, it's always going to be the same, because I'm essentially dealing with means of a bunch of realizations. But the underlying idea is that if I were able to identify individuals in the population and I looked at them, I would observe that their time of sojourn, their lifetime, is exponentially distributed. So there is a probability distribution function underlying this differential equation, even though when you write it, you're not thinking about things that way. If I have a Dirac, then my survival function is this, and then the model simply takes this form. I survive with probability 1, everybody survives until time omega, and nobody survives past time omega. Okay, so here, and prime is 0 everywhere, except at omega, because omega I have my spike, and there it's not defined. But this is another extreme. Okay. Now, let me look at this in the context of an epidemic model. So I'm going to look at a very simple SIS model. So let me move this out here, perhaps. So I'm going to use the same type of SIS model that we used in the first Math-EP lecture, except that here I'm going to assume that there is no demography, the population is constant, and I'm going to tweak the model. And so I should point out I also have mass action, not proportional incidence. And what I'm going to do is I'm tweaking the model. Instead of using a gamma I, as we've done in the past, I'm going to say that there is a proportion P of t of individuals. That function describes how people spend time in I. Okay? So, in practice, what does that mean? It means that, so individuals who became infective at time t0, well, a fraction P of t minus t0, for t greater than t0, is still infective and infectious at time t greater than t0. Okay? So I'm going to look at individuals as they come into the I compartment, and for each cohort, for all the different t0s that are going to happen, I'm going to say that P of t minus t0 is still alive in the I compartment, so it's still infectious that time later. Okay. So when I do so, well, first, before I start, let me make things simpler. So I said the total population is constant, so that means that I can take S to be n minus I, and I can just use one single equation. It will be much easier here. And now let me write the model. So that model is a bit more complicated than the models we've seen so far, so let me spend a little time to explain it. It's going to take the form of an integral equation. And so this system is going to be very simple. Remember, I'm just looking at I because I can get S as n minus I. So this equation 10 includes two parts and three components, essentially. Okay? So we're going to say that at time t, the number of individuals who are infectious is this number here. That's the number of individuals who were infectious at time t equals 0 and are still infectious at time t. Okay, so when the model starts, I have to have some infectious in the population. Okay, otherwise I'm going to remain identically 0. But I have to have some people that are still infectious. I have to initially have people that are infectious, but as time progresses, of course, these people are going to recover. So I0 of t is the function that describes this. So typically, I'm going to assume that it's a non-negative, non-increasing function, and that its limit when t goes to infinity is 0. Actually, I probably should make sure that it becomes close to 0 quite quickly if you want to think about it. Suppose that you stay infectious for 5 days on average. When t is equal to 10, I probably shouldn't have a lot of I0 of t remaining. But that's the sort of generic assumption. And then if you look at this term, it's the product of two terms. So let's start, actually I'm dividing by n here. I thought I was doing mass action, but I'm not doing mass action. Never mind, it amounts to the same thing. So this is infection at time u, for u varying between 0 and the current time. So this tells me that, so this is S, okay, so this is beta Si over n. And this is simply saying that the number of new infections at some time u in the past was a function of how many people were susceptible at the time and how many people were infectious at the time. So this is simply saying that the infection that happens at a given instant in time is beta Si over n. And this is multiplied by P of t minus u. And P of t minus u is the proportion of individuals who became infective at time u, but are still infective at time t. Okay. And I then integrate this over 0 to t. So that means I'm varying u from 0 to t. And this is simply saying how many infections occurred at a given instant u, and how many of those people that became infected at time u are still infected at time t minus u. So just a remark, for example, let's take a simpler, well, not the simplest case. Suppose I take u equals t, then this is essentially what infection is happening right now, and P of t minus u, but when u is equal to t, is P of 0. And remember that a survival function is 1 at 0, because it's the initial moment when you become something, and so your probability of being there is just 1. And so you see how this term comes. Okay. Now, yes, here I'm doing the same description, so let me skip over this if you want to read a little bit more to see what's happening. Now let me do what I did before. So let me start by supposing that the function p of t is exponentially, that the time is exponentially distributed, therefore the survival function takes this form. Okay, and I'm going to assume that the time that you spend in I is has parameter gamma, exponential distribution with parameter gamma. So the mean is 1 over gamma. Okay, so my survival function then takes this form. And the initial condition, I'm going to take something like this. Okay. Then my equation 10, that was before, this equation here, now becomes the following, where I've replaced I0 of t by this expression, and I've replaced P of t by E minus gamma. Okay, gamma t. But it's P of t minus u, so it's E minus gamma t minus u. Okay, so look at this expression, and now take the time derivative of this expression. Then, okay, so you do a chain rule and a variety of things that come in. You're taking the derivative of an integral, so it takes a couple of steps, but what is important is you find this here. And this, again, like we saw in the cohort model, this is I of t. Okay, it's the initial expression. And whatever this is. So what we get is a minus gamma I of t beta Si over n. And that's what ODE I would have for an SIS model with no birth and death, and proportional incidence. I should go back and edit this to make this proportional, but never mind. So this is important. Okay, so here again, I'm observing. Oops, I'm in the middle of a competition. I'm observing the same thing as I was observing in the cohort. So I have a differential equation for the evolution of I that is a very classic one, okay? But that is telling me that when I'm doing this this model where I prime is equal to beta Si minus gamma, I am making the assumption that individuals are spending an exponentially distributed time period in the I compartment before they recover. So that means that there's again an assumption on the distribution of times that individuals spend in I that is assuming that this is a stochastic context. Okay. If I take a step function, the idea is a bit the same. So here I'm going to replace my p of t by this simple function here. In this case, here I should have, I didn't write it here, I should probably have a function that similarly to p of t just assumes that it's I of 0 until time omega and nothing afterwards. Yes. And now when you differentiate, what you get is a delay differential equation, okay, that involves t minus omega in the solution. So the Dirac, I should move myself out, the Dirac distribution, the constant survival for omega units of time, this results in a delay differential equation. Okay, so I hope I've convinced you that the time of sojourn in compartments plays a role that's really important in determining the type of model that you have. And really, I think the main point here is that if you're looking at an ODE, then and a compartmental model for ODE, then you're making the assumption that if you have a term of the form kx going out of the compartment, then what you're doing is you're assuming that the time in the compartment has an exponential distribution. Okay. Delay differential equations come out of assuming that you have a Dirac distribution for your random variable. And I'll point out that both can be true, but reality is somewhere in between. So in particular, that's an interesting thing, because oftentimes people justify using delay to say that delay, when ordinary differential equations only involve the present, which is true. But you have to, this sort of should make you realize that if you're using a discrete delay, you're making the assumption that every single individual in your population survives in whatever compartment you put your delay on for exactly the same amount of time, omega. Okay, that's also a very, very strong assumption. Afterwards, of course, if you use distributed delay or more complicated delays, this becomes much better. But a single discrete delay is also a very strong assumption, and not necessarily one that is very realistic either. As I said, distributing the delay instead of considering it to be fixed then resolves this problem. One problem, let me illustrate one big problem with the exponential distribution. So here I'm plotting the survival function for an exponential distribution where I've taken the mean to be 80 years. So when you're writing a model for an ODE model for an SIR model, for instance, and you have demography, typically you would say, yes, the average duration of life is 80 years, in whatever population I'm looking at, and therefore I'm going to use a death rate to be d equals 1 over 80 years. Well, that's good, and it works in a mean. So that means, on average, your individuals will survive an average of 80 years. But this is what the survival function looks like. And so you can see two things. First of all, this means that when you're using this, you're saying that, so if I go to 20 years, for instance, you're saying that less than 80% of your cohort, if you're looking at a cohort of individuals who were born on time zero, less than 80% of them are still alive after 20 years. That's quite an attrition. Remember, I was talking about the hazard rate and the fact that the most dangerous years are the first few, but once you've survived, you tend to survive well, at least in the 50s or something like this. Well, that means that more than 20% of the population has died in those first 20 years, which is too much. And the other end of the spectrum is also important, because here, if you look, this is 20% of the population. So here I have close to 25% of the population that's still alive at 120 years. Okay. So it really depends what you're using your model for. If you're looking over the long term, what's going to play a role is the average of this distribution. Okay? And that is going to be quite realistic, because on average that's going to be this. But if on the other hand I'm looking at something that's happening quickly, so this is for duration of life, but you can imagine that things are the same if I'm talking about the incubation period. If I'm interested in the short-term dynamics of things, then this becomes probably an issue. So, as I said, like survival drops quickly. Survival extends much further than we would like it to be. It's a problem when you're looking at short-term dynamics, probably, because if you're describing the short-term dynamics, then you're probably not doing a good job. Okay. And yes, another aspect that I didn't mention this far is that if you have an exponential distribution also, one of the annoyances of the exponential distribution is that it has the same mean and standard deviation. So the same mean and the square of the variance. The mean and the variance are given by this, and so the standard deviation is the same as the mean. And so you have a single parameter that's controlling both the mean and the dispersion around the mean, and that's potentially an issue. So let me quickly show you one way to remedy this without going into much more complicated survival functions, and that's I'll call this making Erlangs. So this is a paper that I wrote with a collaborator on COVID, and one thing that we wanted to potentially incorporate is distributions of time spent in classes that would be a bit more realistic, because it's what I was saying before. It depends what your aim is, and if you're looking at a short, we were using this model sometimes to do some short-term prediction of COVID numbers. If you're looking at this type of thing, just saying that the average time that people are infectious, for instance, is 4 days, means that there's this there's this big attrition at the beginning and this long survival that is built in your model. But there's a nice property that allows to work around this, and this is something that the exponential distributions have. And the idea is that if you have identical and independent and identically distributed random variables of exponential types, then the sum is what's called an Erlang. So let me show you this briefly. Suppose I have two random variables, both exponential, and they've got rate parameters, and they're independent. Okay, that means what happens with one doesn't influence the outcome of the other. And they've got rate parameters theta 1 and theta 2. Then if I'm looking at the probability density function of the sum of those, I get it using the convolution. So the convolution product is here. Okay. So the distribution of the sum is simply the integral over the real line of the density of the first multiplied by the density of the second evaluated at z minus x1. Okay, so z being the one that I'm looking at here. And so doing the computation, we find the following. We find that if theta 1 and theta 2 are not equal, then we get this sort of messy expression. But if they are equal and equal to some value theta, then we get this. And this is an Erlang distribution with shape parameter 2. Okay, so this is what an Erlang distribution looks like. And if I look at this expression that I just found, then I have a shape parameter 2 and a rate is called rate parameter theta. Okay? So if the rates are equal for the exponentials, so if they're IID, oops, I should move myself out. If the two exponentials are independent but identically distributed, then what I get is their sum follows an Erlang. Okay, and it actually continues, and so if I take n IID random variables that are exponentially distributed with parameter theta, then their sum is Erlang distributed with parameter theta and shape parameter n. Okay. An Erlang is, oops, I should get out of the way. An Erlang is a gamma. Okay, gamma distributions are very well known, and an Erlang is a particular case of a gamma in which the shape parameter is an integer. It's got a mean of k over lambda and a variance of k over lambda squared. We know what the cumulative distribution function looks like, and we can compute also a survival function. Okay. And we get something like this. So here I'm showing you an exponential, and here I'm showing you an Erlang with shape parameter 2, so 2 compartments if you want, and here an Erlang with 8. And so how do you use it? Okay, maybe before I show you this, let me see if this works. Oh yes. So this is, by the way, I will show you how to work this type of, this is a shiny app running on some remote server that is called by the slides. Okay? I will show you how, when I describe R, I will talk about making this type of thing. So here, what I want to stress is, okay, so here I'm showing you the probability density function and the survival function. And what I want to stress is, okay, so when I increase the number of compartments, you can see, so this is so a shape parameter of the Erlang, and you can see that the function moves more and more to the right here, and survival stays quite high for longer and drops down to a much lower value faster. Okay, so that's if I'm using 20 compartments, for example, this is what I get. Okay, and so how would you use it? So I need to move to the next slide. how do you use it? Well, it's let me show you with this example of the model I was talking about before. So the idea is that if I add compartments, I get this error. So I'm thinking in terms of the time of sojourn in groups of compartments. So this is an SLIAR model. Except that what is happening here is that both I, A, and L have, in this case, two compartments. So what this is saying is that, and so we're focusing here, I've made the rates the same. You see this epsilon here is the same for L1 and L2. The gamma is the same for I1 and I2, and actually also A1 and A2. So that means that instead of considering a single compartment in which the exponential, in which the sojourn time will be exponential, I'm considering the two compartments together. And the time of sojourn in those two compartments, because they have epsilon here and epsilon here, it means that the time of sojourn is an Erlang with parameter, shape parameter 2. Okay, so all I need to do is revise my mean. So because the mean now is different, it will be n over lambda, but I can recompute the mean. If I want my mean to be 4 days, for example, I can recompute this given the lambda, the n over lambda that I want, I know I want, and the n that I'm fixing equal to 2. And so instead of having this case that I'm this exponential here, for instance, I would have a distribution. So suppose the incubation period I'm looking at, so let's say incubation period is 4 days. Well, if I use a single compartment and I assume that the average time is 4 days, this is the type of distribution, the blue one is the type of distribution I would have, and the survival would be like the blue here. Whereas by assuming two compartments, the mean, so the time that I spent in those two compartments together has a distribution that is like that red one here, and like this Erlang here. And I could make, so we tried, and it didn't make much difference, but we could probably, for instance, go up to 8 compartments. And then if you have 8 compartments, you see that your curve is shifting here, and the curve becomes much more pronounced in terms of the survival. Okay. So that's it for this. Now, quickly, let me briefly go over the types of stochastic systems. I'll come back to this later. So the first type that became quite popular was, for instance, the Reed-Frost model. So that's what's called a chain binomial model. So this is from around the 20s, and the idea was you have individuals, infection that spreads from the eye to others after an adequate contact. And it was formulated this way, so S after infection, after contact with an eye, develops the infection, and is infectious to others within, in that case, in the Reed-Frost, it's the next time period. And after having been infectious for one time period, they become recovered. And there's a fixed probability of coming into adequate contact with other individuals, etc. This generated a lot of work. So Reed-Frost models are, if you look at the probabilistic literature, they generated quite a lot of interest. Since probably that's the domain that's been more active, for instance, in the 50s, in the 1950s, than were deterministic epidemic models. Discrete time output chain I will discuss in much more detail later, so I'm not going to spend some time here. It's very much like the discrete time deterministic system, but it does include stochasticity. And there's a memoryless property that your next state only depends on where you are currently. It's fantastic to study using linear algebra, but I'll come back to that. Continuous time Markov chains are essentially equivalent to VODs, and I will show you this because I think it's a very good system to study. They're harder than discrete time, but they're still amenable to analysis. Another type that I'm not going to cover is what's called branching processes. They're essentially a bit like continuous time Markov chains in a continuous case. There's actually an equivalence between some types of continuous time Markov chains and some continuous time branching processes. We'll get into this. This is typically used to describe things that can, for instance, if you have births and deaths processes. And finally, stochastic differential equations that I'm not going to detail in the course here. Typically, it is the adjunction of a deterministic part and a stochastic part, where the stochastic part is influenced by something like, for instance, the Wiener process. And as I said, I'm not going to detail this.